Assalamu alaikum students. Welcome back to the CC4 to 3 lectures on projection. Now we'll look into perspective projection. For this lecture, I will look into the simple purpose perspective projection, which is a very specific version of perspective projection. Now, I hope you already know what perspective projection is. In case of perspective projection, the projectors or the projection rays converge into a central point, which is known as COP, a center of projection. Here you can see this diagram. This square-shaped flat plane is the projection plane. This cube is our object. The object has many points, so we can refer to this point as P, and the projected point on the plane is P prime, as seen earlier. So this is a coordinate system. This is the Z plus axis, X plus axis, Y plus axis. The opposite sides indicate the negative side of each axis. And on this corner, you can see the simplified 2D version of this diagram. So it also indicates the axis and the COP and the P and P prime. And the projection plane is indicated by this inner edge of this triangle. All right. And the distance between COP and the projection plane is indicated by D. This triangle base indicates the Z-axis. All right, we should remember this. And so when we use simple purpose, it's for perspective projection cases only when the center of projection or the COP is on the Z-axis. So this baseline was the Z-axis, and the COP needs to reside on the Z-axis. So it means it can have a Z component value of whatever. It can be positive or 0, but it cannot have any X or Y component. So their X and Y value must be 0, 0. So their Z value can be anything, but their X and Y value must be 0. While calculating projection, we essentially calculate the P prime point, or specifically the X prime, Y prime, or Z prime, the three components that constitutes P prime. All right. And we're given the X, Y, Z coordinates of the point P and some configuration regarding the distance between the COP and projection plane and where the COP is located. Let's recall some formula from our school. We already know some formulas regarding triangles. On the right, we can see this diagram from the previous slide, but with the vertices labeled with letters. The COP is labeled as A, the projection plane center is B. So AD is actually, or AB is actually the Z-axis as said previously. BC is the projection plane, and E is the point where our target point, and C is the projected point. So what we can see is essentially a smaller triangle called ABC inside a larger triangle called ADE. And with the triangle formula for edges, we can say BC divided by AB equals to DE divided by AD. So BC being these perpendicular lines, and ED also the perpendicular line here, bigger one. AB is the baseline, smaller baseline, and AD is the larger baseline. For simple purpose perspective projection, we usually look into two cases where the COP or center of projection is at origin, and another one where the PP or the projection plane is at origin. First, we will look into the first case. In this case of where the COP is at origin, we will indicate each point with their components separated. So X, Y, Z values for each points, A, B, C, D. So our COP was this A point. So since the COP is at origin, this A point is 0, 0, 0. Now, as I said earlier, this left side indicates the positive X direction, and this right side indicates the negative X direction as indicated by this gizmo here. And since this is the origin, everything right to it has a negative Z value inherently. So this B point here, it has a negative D, this D value is negative. Same applies to this the XYZ point here. So this Z is negative. This Z prime is also negative. We'll now apply this statistic formula from our school, BC by AB equals to DE by AD to each of these components individually. So we apply this formula for X, Y, and Z separately. For the X component, if we consider BC first, so BC is here, this line segment, we will take the difference between B and C, which is X prime. And by AB for AB, for the X component, we will take this distance, which is indicated by AB as here, equals to, this for this ED, we're taking the X difference, X minus 0 is X, and also for AD, we will take this the baselines difference as Z, right? We also do the same for Y and also do the same for Z. So we will get three equations, and what we will do now, put the prime parts x prime, y prime, and z prime on one side. So for this case, so we will take them into the left hand side and put everything else on the right hand side. So we will get these three equations. If you notice these equations carefully, you can see these three equations have their denominators as a common value. So they all have z by d as their denominators. We will indicate this z by d as w, right? So since they have a common denominator, we can replace them, substitute them with w. So denominator is w now. We can move this denominator or w actually to this left hand side, which we have done here. So w is on the left hand side and everything else is on the right hand side. X prime into w is this x, y prime into w is y, z prime into w is z. And we are also making w its own equation, w equals to 1 by d, which is equals to z by d. We can now use this formula to calculate x prime, y prime, and z prime, but our target is to build a matrix because matrix is easily composable with other transformations. So before we do that, I have, for your convenience, I have color coded each of these of the terms coefficients with a specific unique color. So x component coefficients is labeled as red, green, y is green, z is blue. This is also a z term, so it is also blue. Now we can build a matrix, but how we can build a matrix? Using this strategy, where if you have four set of equations of four, we already have a set of equations like this: x prime into w, y prime into w, z prime into w, and w. And on the right hand side, if you have structures like ax plus by plus cz plus d, we can restructure these equations into a matrix multiplication system where in the matrix we store only the coefficients and it multiply with the column vector where we store x, y, z and 1. Since this is a homogeneous coordinate system, there's a 1 here. And it will, if we multiply this, it will give us the x prime into w, y prime into w, z prime into w, and also a w. All right. Using this strategy and our equations from earlier, we can now build the actual matrix. As shown here, we are placing these coefficients into the matrix and it will give us this nice little matrix. It is quite similar to the identity matrix, but here look into here, there is no 1 here, and in this part there's 1 by d. All right, so to perform simple purpose perspective projection in case of where COP is at origin, we only need to know the d value or the distance between the COP and the projection plane. Now we will look into another case where the projection plane itself is at origin. So we will look into this diagram from before. So we already know the distance between the projection plane and this COP is d, indicated by d. We'll take it into mind. And this base of this triangle is the z-axis. So every x and y values on this baseline is 0, 0. And since the projection plane is at origin and this b point is indicating our projection plane center, so the center values of coordinates are 0, 0, 0 since the projection plane is at origin. Everything left to that has a positive z value and everything right to that has a negative z value. So as I said earlier, the distance between the projection plane and the COP is d. So if we add the d value to this origin, we'll get our COP, which is 0, 0, d. So since this d is inherently positive, and this z here is inherently negative from before, this applies to this z also. This z and this z is the same. And the z prime, now the z prime is not positive or negative. This is actually 0 since it is on the same plane. So the C point or the projected point here and the center of our projection plane, they are on the same plane. So their z value is also same. So the z prime is 0. So will our user transfer formula BC by AB equal to DE by AD, just like before in this scenario as well. So x prime, which is BC by D, which is AB, equals to x, which is this AD edge. And now for this 80 part, we'll negate d, we'll negate, so d minus z equals to 80. So we'll rearrange on this part so that x prime becomes isolated. We'll apply the same formula for the y prime, and y prime becomes isolated here. So in our denominator, if you look here, we'll get d minus z by d, which we can rearrange into 1 minus z by d. And since for this z prime, there is no denominator here. If we can imagine the same denominator here, 1 minus z by d. But if we put 0 in the numerator, it becomes ultimately 0. And since it is also already 0 because it's on the same plane, and our plane goes through the origin, so z prime is 0. We don't need to write the denominator here. All right. So as we said earlier, we are naming our denominator always as W and moving W to the left hand side. Our denominator here is 1 minus z by d. So we will move this 1 minus z by d for this each of these three equations to this left hand side. So x prime into w, y prime into w, z prime into w, which will also result in this case 0, so which we done in the next slide. So x prime into w equals to x, y prime into w is y, z prime into w is 0, and w itself, its own equations, becomes minus 1 by d into z plus 1. Here I have written it component wise and color coded their coefficients here, like just like before. So in this equation from z prime into w, there's no x prime x term, y term, or z term, or not even a leftover term. So it is 0 here. Here in this equation, there's only an x term. For the second equation, there is a y term, and this fourth equation for w, there's a z term and a leftover term. So leftover term is indicated with purple color. Now we have separated our coefficients and color coded them. We can now build the actual matrix. So we use the same strategy for this here as well. So we have a second set of equations of 4, x prime into w, y prime into w, z prime into w, and w itself. We'll group all these coefficients into the matrix and multiply that matrix with our x, y, z homogeneous coordinate column vector, which you have done here. As you can see, it's also similar to our identity matrix, but here it is 0 here, and in our previous version where the COP was at origin, there was 1 by d, but now here it is minus 1 by d. So both of the matrices are similar, but there's a small catch here. There is 1 here. Previously it was 0, and previously it was 1, and now it is 0 here, and it is negative 1 by d here. We got to know the projection matrices for both cases of simple purpose perspective projection. One case for COP at origin and another case at where the projection plane is at origin. Now let's look at some examples. So our first example indicates a case where the COP is at origin. All of our projection math has the same goal, to calculate the projected point of P prime from a given point called P. So our given point here is 50, 60, minus 30. And COP is at origin, and it also gives us the distance between the projection plane and the COP. So now, since the COP is at origin, so the COP point is 0, 0, 0, this point here on the base of the triangle. So as I said earlier, this base is actually the z-axis. Everything on the z-axis has an x value of 0 and y value of 0, but their z value varies. So everything right to this COP point, since the COP is at origin, has a negative z value. For this 0, 0, d point, or this base of the projection plane, or the center of the projection plane, is there. Its z value is negative 200. As said earlier, the distance between projection plane and COP is 200. This smaller h indicates our projection plane, or at least a portion of our projection plane. The P prime point, our projected point, will appear on this plane. So it is here. And our target point, which is P, is here, 50, 60, minus 300. And as I said earlier, the d value here, so this point was 0, 0, d. We were putting the z value of projection plane. So this projection plane is 200 units in the negative axis from the COP. So it has a negative z value of minus 200. Okay, all right. So you have got to know why d is negative here. Now we'll put the d value into the matrix for the COP of COP at origin matrix and perform the actual math. So we put the negative d values here. So the formula was like an identity matrix. This corner here was 0, and this part was 1 by d. Since the d value is negative, so 1 by minus 200. And what you need to do is our target point was 50, 60, minus 300. We arrange this point into a column vector here, 50, 60, minus 300, and 1, since it is a homogeneous system. If we multiply this projection matrix and our column vector as our point, we'll get this column vector here, which is a 4 by 1 column vector, and our matrix, which gives us the 50, 60, minus 300, and 3 by 2. And notice here, this W term here is 3 by 2, or 1.5. It is not, this column vector is not our final answer. Our final answer should have 1 in this case. So from our matrix system, so we have seen this is our W term. on the fourth term was w, and each of our x prime, y prime, and z prime, which have w as their factor of w multiplied with them. So we need to divide each of the term by w. So we have done here. We have divided 50 by 3 by 2, and we have got 33.33. We have divided 60 by 3 by 2. We've got 40. Divided minus 300 by 3 by 2, we have got minus 200. And we are also dividing w by itself. So 3 by 2 divided by 3 by 2 gives 1. So this is our final column vector. So from this column vector, we can get our projected point. So this is our 33.33, 440, minus 200 is our projected point. So this is our first example. Let's look into a second example where the projection plane is at origin. In this example here, it is given that our targeted point is 50, 60, minus 100. It's quite different from our example before. So the P point appears here. The P prime, or the projected point, appears here as like before. Now, when we say the projection plane is at origin, we mean the projection plane goes through the origin. And this base points, as I said earlier, is the z-axis. So the z-axis pierces through the projection plane. The z-axis actually goes through the center of the projection plane, which is this point. And this point is the origin itself, which is 0, 0, 0. Everything left to that has a positive z value, and everything right to that has a negative z value. So this is why this point it has a minus 100 z value. And for this scenario, our COP coordinate was 0, 0, D. And it is given here, the projection plane is 200 units away from the COP. So the distance between COP and projection plane is 200 units. And since it is 200 units and it is on the z-axis, so our COP is at 0, 0, 200 point. And since our COP is at a positive z side, our D value will be positive. So D is here is 200. All right. So we put the D value in our matrix for our projection plane at origin formula. So it will give us this matrix. So it's like the origin identity matrix, but here it is 0 here. And we put the D value in the denominator in this part. But our formula was minus 1 by D. So since D is positive, so this whole term is actually negative, since in our formula it was negative minus 1 here. So our given point, or P point, was 50, 60, minus 100. So we arrange this point into a column vector, or a matrix of 4 into 4 by 1 matrix. We multiply both of these matrices and get a result of 50, 60, 0. Okay. So why this one is 0? So if we look at this image here, our projection plane goes through the origin. So every z value on the projection plane has a 0 value. So since the projected point itself, P prime, resides on the projection plane, it will have a 0 z value. So this is why the z value here is 0. The w value here is the 3 by 2, which is 1.5. So we need to divide each of the term by w, which is 3 by 2. So we have divided 50 by w. We have got 33.33. And same for the y component, so we got 40. 0 divided by 3 by 2 is 0. And w divided by w, which is 3 by 2 divided by 3 by 2, gives 1. So we've got our final column matrix. Now we can rearrange it to our coordinate system, where is our final answer is 33.33, 40, and 0. I hope these two example covers those two scenarios where we do full purpose perspective projection. This type of perspective projection, this specific type, is only used when the COP, or the center of projection, is on the z-axis. But every other cases, like when the COP is not on the z-axis, like it has a x and y values that's not 0, we cannot use these formulas or these two scenarios. We need to use another type of system where we can use arbitrarily COP positions. It's called a general purpose perspective projection. We'll discuss it on our next class. Till then, take care. Assalamu alaikum.